Hello, everyone. Today we are going to talk about genetic quantization-aware approximation for nonlinear operations in transformers. Slide 1. Motivation: highlight the need for optimizing nonlinear operations in transformer-based models due to their high computational cost. Discuss how the inefficiency of nonlinear operations hinders the speed-up of transformers on various hardware platforms. Emphasize the need for a more efficient and general LUT approximation framework that can handle integer-only quantization. Slide 2. Related works: discuss previous works that have approximated nonlinear operations using quantization-aware 32-bit integer int32 arithmetic. Introduce the neural network-based general LUT approximation framework called nitrogen mononitride LUT. Discuss methods that simplified the LUT approximation by factorizing floating-point data and performing single-entry LUT approximation on the mantissa in a small range. Slide 3. Limitations of existing approaches: discuss how existing methods lack generality as each optimized operator contains distinct computational data flow. Highlight how the LUT contains numerous parameters that are independent of the input data range, leading to resource wastage. Discuss the struggle of NN-LUT to encapsulate the variation in the representation range across layers unless subjected to calibration, a process that is time-consuming. Slide 4. Need for a new approach: discuss the need for a new approach that can overcome the limitations of existing methods. Highlight the need for a method that can handle larger scaling factors and is efficient in hardware design with compact resource utilization. Discuss the importance of capitalizing on low-bit integer arithmetic in the new approach. The authors of this paper are addressing the challenge of optimizing nonlinear operations in transformer-based models. This problem is significant due to the high computational cost associated with these operations, which hinders the speed-up of transformers on various hardware platforms. Previously, this issue was not adequately addressed due to the lack of generality in existing methods. These methods approximated nonlinear operations using quantization-aware 32-bit integer int32 arithmetic, but each optimized operator contained distinct computational data flow, limiting their applicability. Additionally, the existing LUT approximation framework, NN-LUT, contained numerous parameters that were independent of the input data range, leading to resource wastage. The nitrogen mononitride LUT also struggled to encapsulate the variation in the representation range across layers unless subjected to calibration, a process that is considerably time-consuming. To improve upon these limitations, the authors introduced a new approach, a genetic quantization-aware algorithm called GQA-LUT. This method automatically determines the breakpoints in LUT approximation for nonlinear functions, overcoming the constraints of existing quantization algorithms that fail to adjust parameters by scaling factors. To manage larger scaling factors, the authors implemented an algorithm that images the fixed point, FXP conversion, as a form of mutation to boost accuracy. This approach is designed to be efficient in hardware design with compact resource utilization, capitalizing on low-bit integer arithmetic. The author's in-depth analysis of the integer-only quantization scheme and LUT approximation revealed that the scaling factor in quantization is a crucial element that significantly impacts the precision of approximation parameters. They found that larger scaling factors lead to less accurate approximations, a key insight that informed the development of their proposed method. The GQA-LUT method demonstrated significant improvements in performance, maintaining fine-tuning accuracy for both seg-former B0 and efficient VIT BO with minimal loss. Compared to nitrogen mononitride LUT, the GQA-LUT achieved improvements of 1.07% and 0.88% for these models. These results underscore the effectiveness of the author's approach in addressing the identified problems with existing methods. Section 1. Problem formulation and approach. The authors identified the inefficiency of nonlinear operations in transformer-based models as a significant challenge. They noted that existing methods for optimizing these operations, such as the nitrogen mononitride LUT framework, lacked generality, and were resource-intensive. To address this, they proposed a new approach that focuses on the interplay between the scaling factor and LUT parameters. They formulated a general, quantization-aware LUT approximation computing flow, which takes into account the scaling factor in quantization, a crucial element that significantly impacts the precision of approximation parameters. Section 2. The GQA-LUT method. The authors introduced a genetic quantization-aware algorithm, GQA-LUT, to automatically determine the breakpoints in LUT approximation for nonlinear functions. This method is designed to be efficient in hardware design with compact resource utilization, capitalizing on low-bit integer arithmetic. To manage larger scaling factors, they implemented an algorithm that images the fixed point, FXP, conversion as a form of mutation, to boost accuracy. This approach is a significant departure from previous methods, which struggled with large scaling factors and lacked the ability to adjust parameters accordingly. Section 3. Experimental design and improvements. The authors designed experiments to compare the performance of GQA-LUT with the previous state-of-the-art work, NN-LUT. They evaluated the operator-level accuracy for a variety of nonlinear functions and the fine-tuning accuracy of two models, segformer and efficient-VIT, in the context of semantic segmentation tasks under integer-only quantization. The results demonstrated that GQA-LUT with surpassed nitrogen mononitride LUT in both operator-level performance and fine-tuning accuracy. Furthermore, the int8 hardware units integrated into GQA-LUT yielded significant savings in area and power dissipation compared to their high-precision counterparts. This indicates that the author's approach has improved the efficiency and performance of nonlinear operations in transformer-based models. Technical results. 1. The proposed GQA-LUT method was tested on two models, segformer B0 and efficient-VIT BO, to evaluate its fine-tuning accuracy. The results showed that GQA-LUT effectively maintained the fine-tuning accuracy for both models with minimal loss of 0.07% and 0.02% respectively. This demonstrates the effectiveness of the GQA-LUT method in maintaining model performance while optimizing nonlinear operations. 2. When compared to the existing nitrogen mononitride LUT method, the GQA-LUT achieved improvements of 1.07% and 0.88% for segformer B0 and efficient-VIT B0, respectively. This indicates that the GQA-LUT method not only maintains model performance, but also enhances it compared to existing methods. Implications of results. The results imply that the GQA-LUT method is an effective solution for optimizing nonlinear operations in transformer-based models. It not only maintains model performance, but also enhances it, making it a viable alternative to existing methods. Furthermore, the GQA-LUT method's ability to manage larger scaling factors and its efficient hardware design with compact resource utilization make it a promising approach for deploying transformers on edge devices. Ablation studies. The paper does not explicitly mention any ablation studies. However, the comparison of GQA-LUT with the existing nitrogen mononitride LUT method can be considered as a form of ablation study. The results of this comparison showed that GQA-LUT outperforms nitrogen mononitride LUT in terms of fine-tuning accuracy, demonstrating the effectiveness of the proposed method. Implications of ablation studies. The comparison with nitrogen mononitride LUT highlights the advantages of the GQA-LUT method. It shows that the proposed method can effectively optimize nonlinear operations while maintaining or even enhancing model performance. This suggests that the GQA-LUT method could be a valuable tool for researchers and practitioners working on transformer-based models. Key highlights of the paper. 1. Key insights. The paper identifies the scaling factor in quantization as a crucial element that significantly impacts the precision of approximation parameters. It also reveals that larger scaling factors lead to less accurate approximations. 2. Key contribution. The paper introduces a unique genetic quantization-aware algorithm called GQA-LUT. This algorithm is designed to automatically determine the breakpoints in LUT approximation for nonlinear functions. It also proposes an enhancement technique, which images the fixed point FXP conversion as a mutation process. 3. Key idea. The main idea of the paper is to overcome the constraints of existing quantization algorithms that fail to adjust parameters by scaling factors. This is achieved by proposing a method that manages larger scaling factors by implementing an algorithm that images the FXP conversion as a mutation process. 4. Key results. The GQA-LUT effectively maintains the fine-tuning accuracy for both seg-former B0 and efficient VIT BO, with minimal loss of 0.07% and 0.02% respectively. Compared to nitrogen mononitride LUT, the GQA-LUT achieves improvements of 1.07% and 0.88% for these models. Additionally, the INT8 hardware units integrated into GQA-LUT yield significant savings of 81.3 to 81.7% in area and 79.3 to 80.2% in power dissipation compared to their high-precision counterparts. 5. Key conclusion. The paper concludes that GQA-LUT with surpasses the previous state-of-the-art work nitrogen mononitride LUT in both operator-level performance and fine-tuning accuracy. The proposed method paves the way for efficient hardware design with compact resource utilization, capitalizing on low-bit integer arithmetic.